it's really a success, I would say, today's lunch. And it's our great pleasure from the Quantum Science Center at EPFL to have Professor Patrick Potts with us today. He comes from the University of Basel, where he's an SNSF Excellenza professor, running his own group in theory of quantum systems. He's going to tell you more about it today. Patrick did his PhD in Geneva. After studying in Basel nanosciences in his bachelor and physics in his master, so he saw quite a variety of subjects throughout his career. Then he did, during his PhD, also spent some time in Canada at McGill University, and he did a postdoc in Sweden. And with that, I give the floor to you, Patrick.
Thank you very much, Christina, for the introduction and also for the honor of kicking off this new seminar series. So it's a pleasure to be here. And I will talk about non-classical behavior in open quantum systems. And more specifically, I'm going to talk about two recent projects that came out from our group. This one actually appeared on the archive this morning. And both of these projects, we investigated transport scenarios. So in the first one, transport of electrons through a double quantum dot, and in this one, transport of photons or bosons through two coupled bosonic modes. So it's really about non-classical behavior in quantum transport. But first, let me acknowledge the team. So this is a picture of the quantum thermodynamics group taken on the rooftop of the physics department in Basel. And the people that were mainly involved in the works I will present today are the PhD students Kasper Prech and Marcelo Janovic, and the postdoc Matteo Brunelli. Let me start by motivating why we are interested in non-classical behavior. And I think there's really kind of a twofold motivation. So on the one hand, it's very interesting fundamental questions we can ask, and there's also a more practical motivation. And so on the fundamental side, we really try to understand the difference between quantum behavior and classical behavior. And I think this is very nicely illustrated in this sketch by Zurek, where we have this border between the classical and the quantum world. And in the quantum world, we have all these non-intuitive features such as superposition and entanglement, and the observer plays a crucial role. And on the classical side, things behave more as our intuition from everyday life tells us. But then drawing this border is actually a very non-trivial task, so exactly figuring out when is something kind of truly on that part of the border or when it's on that part of the border. So on the fundamental side, we really try to understand this border with all its subtleties. And then on the practical side, of course, exploiting quantum effects for technology, as you all know, is a huge program. But also knowing exactly where this border goes through might give us new ideas to exploit such quantum effects also for practical applications. And now to set the stage, so before I talk about the work that we actually did, I would like to talk a little bit about what I mean by non-classical behavior, because that's a very broad term that people use in different ways. And so I want to present a few types of non-classical behavior. So I grouped non-classical behavior in a few types here, which is of course a very subjective grouping, but just to set the stage here before talking about our results. And so the first type of non-classicality that I briefly want to talk about, I call it here fundamental non-classicality, because it is when a fundamental classical notion is violated. And there a very prominent example is the one of Bell non-locality, where a violation of so-called Bell inequalities allows one to rule out any local so-called hidden variable theory. So here the classical notion that is violated is the locality, so a principle of locality, and one can violate these Bell inequality in so-called Bell tests. So this is sketched here, where one has a source that distributes a state between two parties, usually called Alice and Bob, and then they perform measurements locally on their part of the state, and the Bell inequality then tells us if we can rule out these classical local theories or not. And in 2015, 3 experiments came out that show the so-called loophole-free Bell test, and this is a picture of one of these works, where here C is the place where the state is generated, which is then distributed to Alice and Bob, which are situated 1.3 kilometers from each other. So really a quite impressive experiment, and one really needed this separation to rule out any of these loopholes and to really rule out any local theory explaining the results. So the next type of non-classicality that I briefly want to mention is, I call it here technological non-classicality, but it's what many people would call a quantum advantage or quantum supremacy. And it's when a quantum device outperforms state-of-the-art classical devices. And then usually I also put a near future here, just to make sure. I mean, we want the quantum device to be not just be good against the state-of-the-art now, but also against the state-of-the-art maybe in the next couple of years. And so there's this example, which maybe is a little bit infamous by now, where in 2019 on the Sycamore processor, a computational task was performed in 200 seconds, and in this paper it was claimed that, or it was estimated, I should say, that a state-of-the-art classical supercomputer would take 10,000 years for that. But then this computational task that they chose here was very adapted to this particular scenario, and nobody really tried to solve such a task before with a classical. So nobody tried to optimize really classical computers to do the same thing. So a few years later, people came out with a very smart algorithm to solve the same problem in just 15 hours on a classical computer, and they estimated that actually it should be possible with state-of-the-art supercomputers in a few dozens of seconds. And so here, the take-home message for me at least is that this technological non-classicality, or this quantum advantage, should really be established on problems which already stood the test of time. So kind of relevant problems that people already tried hard to solve. Because if we design our problems just to show a quantum advantage, then there's absolutely no guarantee that there won't be a very near future classical device which can outperform our quantum device simply because people came up with a smart classical solution to the problem. The next type of non-classicality is non-classical scaling. So this is when quantum correlations result in a favorable scaling with the number of units. So there a prominent example is from quantum sensing, where one can use like a number of detectors or sensors, and let's say n is this number of detectors. And if we have uncorrelated detectors, then there is this standard quantum limit, which implies that the sensitivity goes as 1 over the square root of n. And this standard quantum limit is surprisingly hard to beat, but one can do so, for instance, using entangled detectors. Then one can reach the so-called Heisenberg limit, which is a limit imposed by the uncertainty relation, where the sensitivity goes as 1 over n. And so this results in a favorable scaling. So if we could, in principle, then have a lot of entangled detectors, then we can outperform kind of the uncorrelated detector case. And so this brings me to the final type of non-classicality I want to mention here, and this will be the kind of the type of non-classicality that the rest of this talk will also be about, and it's when we rule out certain classical models. So when observations cannot be reproduced by an adequate classical model or by multiple kind of adequate classical models. And so to give an example, in quantum optics, one often calls things non-classical when observations cannot be explained by classical electrodynamics. So for instance, this is the Wigner function of a single photon, and you see it has this negative peak here. So people would often call this a non-classical state because it doesn't have an analogy in classical electrodynamics. And of course, then in this example, we just rule out one classical theory, but one can also be a bit more ambitious and try to rule out a full class of classical theories. So this can, for instance, be done using thermodynamic uncertainty relations. So this is an inequality, and I will talk more about this later in the talk, but for now, this is simply an equality that holds for classical Markovian theories. So an example of that would be like classical rate equations, where a system can transition between different states. And when one finds that this inequality is violated, well, then we can rule out all these classical theories for which this inequality holds. And in a sense, this non-classicality here is a bit stronger, a bit weaker than maybe the previous types of non-classicality I discussed, because we're ruling out maybe a single or maybe a few classical models. But nevertheless, I would say we get a lot of insight into the quantum to classical transition, as for instance illustrated with the example of quantum optics, where we really kind of can probe like until where does our electrodynamic theory of light work, and from when do we really have to, well, our classical electrodynamic theory, and when do we really have to include quantum effects in that theory to explain the data which we believe, because we know the system, that we're dealing with like light and electromagnetic waves. Okay, so this brings me to the next part of the talk, so non-classical behavior in quantum transport. And now I'm going to talk about these two projects as advertised. And in the first project here, we investigated a double quantum dot. So this is a system where there are electrons. The red and the blue part here are reservoirs for electrons, and then they can tunnel into one of these dots. The dots are these lines here, and then there can be coherent tunneling between the dots, and the electron can jump out again. And in this system, we have multiple what we call manifestations of coherence. So quantum coherence can have some interesting effects here. It can result in entanglement and even non-locality, and also in these violations of these thermodynamic uncertainty relation and related inequalities. And here we will also compare to a classical model, so we will rule out a classical model, and this will be a classical rate equation where the electrons kind of cannot be in a superposition between the two dots, but are simply jumping between the dots and the reservoirs and the dot. And in the second project here, we are looking at a quantum heat engine. So here the idea is that a heat flow from hot to cold will generate a power output, and it's a transport of photons here or of bosons through the system that comprise this quantum heat engine. And here we are interested in the wave-particle duality. So we compare like a quantum description of this system to a description based on classical waves, as well as a description based on classical particles. And then we want to get insight like when can the photons here be described as waves or as particles, and when do both of these classical pictures break down. And the overarching question is really, when can transport be described using classical models here. So let me start with the first project. So the bulk of the work here was done by a PhD student, Kasper Prech, in my group. But this was a collaboration with Lund University, the groups of Peter Samuelsson and Claudio Verdozzi, as well as Gabriel Landi, who used to be in Sao Paulo at the time and is now in Rochester in the US. Okay, so the system that we look at here, so here is another sketch of this system, of this double quantum dot. So on the left and on the right we have these electronic reservoirs. They're described by a temperature and a chemical potential. And then the circles here are the quantum dots. And so electrons can jump from the reservoir onto a dot, and then there's a tunneling between these dots, and then they can jump off again. And the Hamiltonian of this system looks like this. So we have the on-site energy terms, which are simply the energy of an electron that resides on one of the dots, and then there's this tunneling term here. And now when one applies a voltage across the system, so a difference in chemical potential or also a difference in temperature, one can generate an electrical current through this system. And due to the coherent tunneling here, we can have these manifestations of coherence that I mentioned before. So you can create entanglement between the two quantum dots. It was first realized in this paper that a similar system can exhibit this entanglement. And this is really quite remarkable, because the entanglement here is induced by the environment which drive a current through the system. So usually the environment, it kind of destroys quantum features such as superposition and entanglement, but here their role is really to drive the current that then creates the entanglement in the first place. Then this thermodynamic uncertainty relation can also be violated in this system. So this was first realized in this paper. And then there's also violations of a similar inequality that I will mention later. And the goal of our work here is really to understand when these different manifestations of coherence appear and when a classical description of the system is just fine. So now let me give you a little bit more background on these manifestations of coherence, so on the entanglement as well as the TOR violations. So starting with entanglement, in general we say that there's entanglement between two subsystems Alice and Bob if the state cannot be written in this way. So this is a combination of product states between Alice and Bob, and it's called a separable state, and if the state is not separable, well then it's entangled. Now in our case, Alice and Bob correspond to the different quantum dots, and we do have entanglement between these dots. We use exactly the same definition. Now in the steady state, the density matrix of the system takes actually a rather simple form. There's lots of zeros here. And on the diagonal you have the probabilities that there is no electron on the dot, that there's one electron on the left dot, that there's one on the right dot, or that there's two electrons on the dot. And then we have this one off-diagonal density matrix element, which corresponds to coherent superposition between the two dots. And with this density matrix, if this inequality is obeyed, so if this off-diagonal density matrix element is sufficiently big, then there is entanglement between the two dots. Okay, so moving on to the thermodynamic uncertainty relation. So I've shown you this inequality before. Now let's look a little bit about the ingredients here. And so they're listed here. So I is the average current that goes through the system. And this object here is called the current noise. And it can be expressed in this way using these two-point correlation functions of the current. And finally, sigma is the entropy production. This is determined by the heat current that goes into the reservoirs divided by their respective temperatures. And this essentially quantifies dissipation. And this inequality is very interesting because it provides actually a bound on the signal-to-noise ratio. So if you take the sigma here on the other side, then what you're left with is I squared divided by the noise, which is a signal-to-noise ratio. And it tells us that entropy production or dissipation provides an upper bound for the signal-to-noise ratio. So if you want to have a large signal-to-noise ratio, you have to allow for a lot of dissipation to happen. And then I also mentioned this kinetic uncertainty relation already. So this is a different inequality that looks quite similar, but now the upper bound on the signal-to-noise ratio is given by a different quantity, which is known as the dynamical activity. And this is a quantity that quantifies like how active the system is, so it can be understood as the average transition rate. So if it's big, then the system moves between states a lot, and if it's small, then the system stays within a given state for a long time. And then people also combined these two inequalities and came up with something more complicated, which is a tighter bound than both of these on the signal-to-noise ratio, and the bound can then be expressed in terms of a complicated function of both these quantities. Okay, now to kind of extract these quantities, so to compute the average current and the noise and also to compute the entanglement, we need to model our system in some way. And we actually use different models here. So one model that we use is non-equilibrium Green's functions, which here for non-interacting electrons that I will focus mainly on in this talk is equivalent to Landauer-Büttiker scattering theory. And then the average current can be written in this well-known Landauer formula. And so these F's are the Fermi distributions of the contacts, and this is known as the transmission function. And being exact here implies that we can calculate this transmission function analytically, but then this integral usually has to be solved numerically. So we can't get analytical expressions out in general for the current and the noise. And in part for this reason, we're also using a different model, which is known as a local master equation, where we look at the density matrix of the system. And then its time derivative is given by two different terms. The first term here is the unitary part. So this is a commutator with the Hamiltonian, and it tells us what's happening within the system. And then the exchanges of electrons with the reservoirs are modeled by these terms here. The first term describes electrons jumping into the system. The second term describes electrons leaving the system. And again, we have a Fermi function that appears here, which is defined here. And yes, so what you can also intuitively understand this because if an electron should enter the system, well, there should be some electrons in the reservoir. If an electron should leave the system, there should be some empty states in the reservoir. That's why you have this 1 minus f here. And finally, as advertised, we also use a classical model to describe this system. So this is a classical rate equation where we have a vector of probabilities for where electrons are and where they are not. And then we have a matrix which includes all the transition rates. And the transition rates describing electrons entering and leaving the system are the same as in the master equation before. But now the coherent tunneling here is simply described also by a classical rate, which one can obtain from perturbation theory. So of course this classical model cannot exhibit any quantum coherence, there's no entanglement, all these inequalities are satisfied. So this is really kind of the model that we want to rule out to show that we have non-classical behavior in the sense that this classical model cannot capture the observations. So let me show you some results now on this system. So what I show you here is this off-diagonal density matrix element, the only off-diagonal element that we have in this problem, as a function of the tunnel coupling between the dots divided by the system bath coupling. So here we take these gammas to be equal and equal to gamma without the subscript. And then note that this is a logarithmic scale, so this quantity changes over many orders of magnitude here. And the black dashed line is the exact result. And then we'll be mostly interested actually here in this peak, where we see that this local master equation that I showed you captures this peak extremely well. And so the reason that we have a peak in coherence here is because coherent tunneling induces Rabi oscillations between being on the left and on the right dot. So we have electrons that kind of coherently oscillate back and forth here. But these Rabi oscillations are interrupted whenever an electron enters or leaves. So if there's 2 electrons here, nothing can oscillate. If there's no electrons, nothing can oscillate either. And now if we have small interdot tunneling, then the Rabi oscillations are interrupted after a very short time, and coherence can't really build up. But then if we increase G, well, more and more coherence can build up. And then we get this peak, because at large values of G, the oscillations actually acquire a random phase because before they are interrupted. And so then we get a phase averaging effect when the oscillations are very fast, and that decreases the coherence again, and that results in this peak behavior here. Again, note it's a logarithmic scale, so this peak looks very symmetric here, but on a linear scale it looks completely different actually. Okay, now the off-diagonal density matrix element is not necessarily the first thing that people in an experiment can measure. So let's look maybe at more relevant experimental observations or observables, which are the average current and the current noise. And again, I show them as a function of the same parameter. And so let's have a look at the current first. So first I should note that the exact solution is here actually hidden. It goes below this curve, and then it goes up here, and then it goes down again. Again, we're going to be interested in this regime here, where this local master equation works really well. And now we also have this classical rate equation, and we see that it simply reproduces the local master equation actually for all parameter values. So when we just look at the average current, then our classical rate equation is just fine to describe this observable. We won't see any effect of coherence here. But this changes when we now look at the fluctuations. So when we look at the noise, here is again the definition, then we see that the exact solution and also the local master equation has this shoulder here, which is absent in the classical rate equation. So in this regime, exactly where we had this peak in coherence, where Rabi oscillations kind of played an important role, there we actually get a reduction in the fluctuations compared to a classical rate equation. And we cannot kind of simply relate this to the off-diagonal element of the density matrix, because we're dealing with noise here. So this is a 2-point correlator, so it depends on 2 points in time, and it doesn't just depend on the steady state. So it really tells us something about the dynamics of the system as compared to just the steady state. Okay, and now we're going to look at these, what we call manifestations of coherence here, entanglement, as well as these violations of the TUR and the KUR. And because entanglement only depends on the state of the system, we call it a static manifestation of coherence. Whereas these TUR and KUR violations, they depend on these 2-point functions, so we call them here dynamic manifestations of coherence, because they really encode something about the dynamics of the system. And this is kind of one of the main plots, I would say, of the paper. So let me guide you through this. We introduce here some quantifiers to quantify these manifestations of coherence. The first one is the concurrence. This is a quantifier for entanglement. And in this system, the concurrence takes a very simple form. It's 0 when there is no entanglement, and the maximal value it can take is 1, which would be the maximally entangled state. And in this plot, it's given by this color scheme, so it's the big blob which lies on the bottom. So wherever we have some color here within this big blob, there is entanglement. Then we also introduce these quantifiers for these violations of these inequalities. So this is the Q that I introduced before, which was bounded by 1. So again, this quantity is 0 when there's no violation, and it's finite when there is a violation. And the red blob here corresponds to violations of the TUR, and the dark blob here to violations of the KUR. And yeah, so the vertical axis is again this G over gamma, and now on the horizontal axis we have voltage divided by temperature. So we assume that the temperature is the same in the two reservoirs. And finally there's this dashed line, and so this illustrates where this TKUR is violated. It's violated between these two dashed lines, and it's not violated outside. Okay, so the first thing we note is that we get all these manifestations of coherence at similar values of G over gamma. They all appear where we had this peak in coherence in the very first plot I showed you. And then the TUR violations, we get them at small voltages. Because small voltages imply we have a small amount of dissipation. And if you remember, in the TUR, dissipation is an upper bound on the signal-to-noise ratio. So if you have a lot of dissipation, it's very hard to beat that upper bound. The KUR is violated, on the other hand, for large values of voltages, because it doesn't really care about dissipation. And you also see that we get more entanglement when we have larger voltages, actually. Because then this off-diagonal element of the density matrix simply becomes bigger as well. Okay, here I also show you two line cuts through this plot, and what you see here in red is again the off-diagonal density matrix element, and this is this peak of coherence I showed you in the beginning, but now on a linear scale, not a logarithmic scale. That's why it's now very asymmetric. And then you can see all these other quantifiers, they really appear where this peak is, and the same for a different value of the voltage. And finally, we also looked at what happens when you now include interactions in the system between the two, between the dots, between the electrons. And so on the very left, I show you the same plot as before. And then when we move to the right, we increase the interactions. And you can see that all these blobs kind of get skewed. The concurrence get this interesting kind of horn-shaped behavior that we don't fully understand why this is the case. And in general, also all the violations become bigger. So we have more entanglement, and stronger violations of this TUR and KUR. And we can understand this in a very simple way. So what the interactions are doing is they prevent double occupation. So they prevent both dots to be occupied. And if that state is occupied, it's more probable that just a single electron is on the double dot. And it's in the single electron subspace where all these coherent oscillations occur. So we're kind of boosting that subspace by preventing another one. And finally, when we have high enough interactions, then the entanglement is actually strong enough that the state becomes non-local, so that it could be in principle used to violate the Bell inequality. Okay, so this brings me to the next project, where we were interested in the wave-particle duality, and we looked at this quantum heat engine. And here we have a quantum model to describe this, and we want to compare this to two classical models, one based on waves, one based on particles, to figure out when do the quantum particles here behave like waves, when do they behave like particles, and when do both of these descriptions break down. And this is the quantum model we use. So we have so this is the Hamiltonian, and we have two harmonic oscillators at two different frequencies. And then there's this coupling term which has a time dependence. And this time dependence can be seen as an external field at frequency delta. And we choose this delta to match the difference of the frequencies of the harmonic oscillators. So whenever a photon moves from here to there, it kind of emits another photon in this classical field, but which is simply modeled classically. And the energy in this external field, we interpret this as power or as work that is produced. And then a temperature gradient kind of drives photons to go from left to right, such that energy is actually emitted into this external drive. And we again use a local master equation, which looks very similar to the one I showed you before for the fermionic system, with the difference that we now have Bose-Einstein distributions. And so this can be understood as absorption from the environment. Here we have spontaneous emission to the environment, and this would be stimulated emission to the environment. So that was the quantum model, and in the wave model, the picture that we have in mind is that we have two kind of classical fields, or classical wave fields, wave modes, and they interact via some chi2 interactions and produce a field at the difference of the frequency. But we want to describe this all classically. So to arrive there, we first kind of rewrite our quantum model. So before I showed you the master equation, but there's actually an equivalent description in terms of quantum Langevin equations, which are simply the Heisenberg picture of the master equation. And there we're dealing with time derivative of operators. And so from the Hamiltonian, we have some terms like this omega h and this coupling term. And from the bath, we have a damping term as well as a noise term. And so this psi here is describing quantum white noise. And it has this kind of correlation function. The Q here implies that we're working with a quantum model still. And then we have this Dirac delta function. That's because it's white noise. And here is where the temperature enters, or the Bose-Einstein occupation enters. And importantly, they obey bosonic commutation relations. And now to reach our wave model, our classical wave model, we simply demote all these operators to classical complex stochastic variables. So we have the same equations, but importantly now these psi's, they describe classical white noise. So we have the same kind of correlation function. The W now implies that we're dealing with a classical wave model. And of course these objects now commute because they're simply complex numbers. And this is the wave model that we use to compare to our quantum model. And then the third model that we look at is the particle model. So here the idea is that we have a number of particles on the left, and they all have energy omega h. And then they can move to the right, and they can kind of turn this gear, and they lose some energy to this gear. And so when they're on the right, they have the energy omega c. They can also go back and kind of get energy from the gear. And the energy that is provided by the gear or that is dumped into the gear is the power. And this process happens at a rate that is exactly the same as we had in the electronic model before. And so here the system is described by a classical rate equation, where the central object is this joint probability of having NH photons here and NC photons here. And this might look complicated, but the first two lines are simply the exchange of particles with the bath, and the rates here are simply taken from the quantum model, from the local master equation. And then finally, here is the kind of the hopping between the two sides, and this is now determined by this rate here. Okay, so now we can compare these three models, and we want to look at the average power and also the noise and the power output, because that's the output that a heat engine gives you. It's the power that it produces. So in the quantum model, the average power is given by this average, and so this is really the energy exchanged with this external field. And then we find that for all three models, the average power is actually the same and given by this relatively simple formula, which can be cast in this way. So we have here the delta, which would be the quanta of the external field, or in the classical wave model, it's the frequency of the external drive. Then we have this kind of bias between the two reservoirs, and this here looks like the series addition of three different conductances, where now this classical rate explicitly appears no matter which model we're actually using. Now the situation changes when you look at the noise. So in the noise for all three models, we can divide the noise into two terms. One is the equilibrium contribution, and one is the shot noise contribution. And the equilibrium contribution, because of the fluctuation dissipation theorem, can be expressed in terms of the average power. So the fluctuation dissipation theorem tells us that equilibrium fluctuations are related to kind of the response in the average, and that's what expressed here. I don't give any explicit equation here for this shot noise contribution, but now we can start to compare them. So if we compare the quantum and the wave model, we see that the shot noise contribution is the same, but in the equilibrium noise, there are these +1 factors missing here. And these really arise from the commutation relation of the bosonic operators, and they correspond to the vacuum fluctuations that we have in the environment. So the wave model, maybe unsurprisingly, cannot capture these vacuum fluctuations, but it correctly captures the shot noise contribution. And finally, the particle model actually correctly captures the equilibrium noise, but the shot noise contribution is different. And so this SP is bigger than S, so here this noise is actually always smaller than the quantum noise, and then we say, well, that essentially classical particles can't bunch as well as bosons, as real bosons. So now let's have a look at this noise, again as a function of the same parameter as usual, the coupling between the modes divided by the system bath coupling. And the blue line is the quantum model, and we find that the particle model given by the red line approximates it very well at large and at small values of g, which is kind of similar to what we've seen in the fermionic case. But then here there's a clear discrepancy where particles cannot properly describe the system. The wave model here doesn't seem to fit at all, but that's just because we use relatively low temperatures for this plot. So in the high temperature regime, the wave model perfectly captures the quantum model. And so what we learn from this is that there are regimes where the bosons here behave like particles. There are regimes where they behave like waves, but there's also a regime where neither a particle nor a wave description actually takes into account what's happening in the noise. In the average power, we don't see any of that. Simply all models give us exactly the same behavior. Okay, this brings me to my conclusions. So we looked at these two projects, and so in this one, in the electronic part, we found that we have these static and dynamic manifestations of coherence corresponding to entanglement and these TUR violations respectively, and we get them for this range of coupling parameters. And here we noted that neither waves nor particles can actually reproduce the noise, while they can reproduce the average. And so one follow-up question now is, for this project here, if we can exploit this insight. Because here the noise in the quantum model is actually always larger than in the classical models. And generally you would like your output to be stable and not noisy. So this seems simply like a disadvantage, a quantum disadvantage. And it might be that that's just the case where quantum is worse than classical. But maybe we can turn this around and find a way to make use of this non-classical behavior in some way. And when we look at this, when we try to adapt these insights to here, then one follow-up question would be to describe the electronic current here using classical waves, so using classical electrodynamics, and to see if we can learn something about non-classical, something additional about non-classical behavior. And quite generally, we would like to apply these ideas of wave and particle models to other setups, like spins or qubit systems, few-level systems, where a kind of a particle-like model is one, would be one, for instance, a model of classical bits or classical few-level systems, and a wave model would be one of small magnets that can oscillate and show some classical coherence, and really kind of using both wave and particle models to benchmark some non-classical behavior. And finally, I would like to have a little advertisement on a tutorial that we wrote recently. So in both of these projects, what we needed to do to get at this non-classical behavior was really to extract fluctuations from quantum master equations. And so if this is something you're interested in, then this might be an interesting resource for you. So with this, I thank you very much for your attention, and I'm happy to address any questions.
Thanks, Patrick, for this really exciting talk. Are there questions? Vincenzo?
Yeah. With the second result, perhaps I have first a very detailed question. So the quantity that you plot, wave, particle, and quantum, is not additive, this quantity here. So it's not that the black line is the sum of the, no, because
no.
Because I see some similarities between this analysis and another recent work, the 1905 work by Albert Einstein, where when explaining actually the work on the works by Einstein and Planck on black body radiation. The heart of those works that is never taught in courses is that Max Planck and then Einstein for the electric effect show that the entropy, which is a statistical quantity like the one that is the sum of two terms. And these terms can be easily understood as the wave-like contribution and the particle-like contribution to entropy. And in the black body radiation, it's beautiful because the actual entropy is the sum of the two. And this, to me, sounds very much like that. So is there any difference, any fundamental difference with that analysis?
So I think, the conclusion of Einstein was that kind of quantum particles sometimes behave as waves and sometimes as particles.
Yeah, that's.
And here I would say, here neither of those is true, right? Here they behave neither as waves and particles. I don't think that's in contradiction to this additivity, because also there you have both contributions kind of at the same time. Here it's not additive, so we were not able to write. I wouldn't claim that shot noise contribution is kind of a wave-like. So here we didn't.
Yeah, because that stimulated my remark, because that quantity there seems to be the sum of different terms. So it may be that at some point you have a particle-like contribution and wave-like contribution that somehow.
Yeah, so we weren't able to identify like a particle contribution or wave contribution here. It was just that waves and particles couldn't reproduce different aspects of the quantum model here. Yes, so in that sense, I guess it's different, but it would be interesting to see if one can make such an identification.
May I ask another one?
Sure.
For the first part, the entanglement that
yes.
You have two spins. Have you tried to see if this entanglement is contextual or non-contextual? So in other words, have you tried to compute the discrete Wigner function of the two spins and see if it's positive or if it has some negativity?
No, we didn't do that.
Okay.
We didn't look at contextuality at all. But that could be an interesting avenue to pursue. Yeah. What would your
because the non-contextual entanglement is the, so to say, lesser entanglement. It's the entanglement that can be simulated classically. Going back to your to the introduction, so non-contextual entanglement can be simulated classically, whereas it's for continuous degree of freedom, it's a Gaussian entanglement. It's Gaussian states that can be simulated with order of.
Yeah.
With order of square. And for spin is the same thing actually. It's the analog, the discrete analogous of Gaussian entanglement for continuous variable. So my question was: is this entanglement of the kind that is very non-classical, or is it of the kind that could, in principle, from the point of view of quantum information, still be simulated efficiently classically?
So my naive guess here would be that when you don't have interactions, then you do have a Gaussian system. It's a quadratic system. So then I would assume that you can still simulate this classically. But when we have strong interactions, then this is out of the window, and then we can really reach also much higher. So for instance, one can reach like higher teleportation fidelities if one would use this state, and one can even reach non-local states. So then I would assume that here we would have some hope to reach entanglement that can't be simulated or cannot be easily simulated classically.
Okay, thank you.
Other questions? Okay, Pablo.
No, you go.
I go?
He was first with the hand.
So just one technical question: why do you need the time dependence in your coupling? You should be able to eliminate it. It's a quadratic equation. Like I understand that the model, like you're a Chi2 element that allows the energy to flow, but then you can eliminate it and pass in the rotating frame.
Yes, yeah, of course.
Okay, so there is no.
No, all the calculations are done in a rotating frame where we don't have to worry about the time dependence. Absolutely, I didn't want to go into this here.
But then I have a second question, maybe more technical. If now instead of considering like the approximation you do to get your wave is to say as equivalently that your state in a, let's say in a p function in some representation is a delta. If now you assume is because essentially you are not taking into account the non-commutativity of your of A and A dagger. That's why you don't see the.
But we do have thermal noise.
You have thermal noise, I agree,
So
but then A dagger commute.
Yes.
Equivalently said in the like it's not equivalent state approximation. You're not projecting on alpha. So
no.
That's my question. If you now do the same wave equation and you suppose instead of a point of a function alpha a Gaussian state, do you get the same? Because like a Gaussian state is as you said at the very beginning is a very classical in quantum optics state. So if now you take an initial Gaussian distribution, so let's say a Gaussian distribution, a classical probability of states, do you get the same? Do you get the same difference between wave and particle? That is my.
So I don't think so. So these guys here, which really kind of drive the system, these are Gaussian, right?
No, absolutely agreed. But then if you do the equation of motion for the second order momenta, quantum, like you ask yourself what is the dt of a dagger square a square, that closes again because the equation is quadratic. So it's a closed set of equations.
Yes.
But then equivalently said, if you just generalize that equation to capture the higher order momenta, you are not accounting for the non-commutativity, for the fact that you have a blob in phase space. From which my question, if you now suppose instead of having a point in phase space, you're supposed to have a coherent state or a Gaussian stat function, do you get, because then it's explainable as, instead of having a single wave, I have a classical distribution of waves. And that you get back the wave behavior. You see my point?
Yeah, I don't think so. I don't think so because for the noise, so if you use these equations of motion, like all normally ordered expectation values will be the same. But whenever you deal with something not normal ordered, then it looks different. Now, if you just look at the higher, kind of at the second, the product of two of those, and try to make those classical, I think you will run into the same problem essentially. And one thing that we try to do is we modified this equality. So here we just put some vacuum noise essentially to say that even at zero temperature these guys have a finite distribution. These are Gaussians essentially with a finite width even at zero temperature. And then you can reproduce the linear parts here, or you can reproduce, but then you get additional constant terms here that are not present. So you can actually come up with other wave models that have a higher noise than the quantum model and maybe work a little better in some regimes, but you can never exactly kind of reproduce this.
Okay, Zoe?
You sure we got time?
Yeah.
Okay, I have a bunch of half-formed questions related to the role of bunching in your second experiment.
Okay, yeah.
Unsurprisingly. So the first one is, to what extent can you attribute the difference between the particle model and the quantum model as due to bunching? Like, have you looked at what happens if you somehow make the photons distinguishable, so you then kind of reduce the effect of bunching?
So how would you make
I don't know. I'm thinking about like carrying different frequencies with different colours. You could have the two different bars, maybe having different polarizations or something. I don't know.
I mean,
I wanted to somehow pin it down.
So
pin down what the different
the photons here, I mean, I guess you would have to make the individual photons here distinguishable.
At the quantum level, I guess. I'm
At
trying
the,
to make the quantum slightly less quantum by changing the particle statistics. I know like Defner's played around with this, like things along these lines. He's managed to somehow attribute things to do with... or you could look at the correlation between the difference and bunching effects. Look at one of the correlators.
Okay, so bunching here is really quite vague. So what people usually refer to is the Fano factor, which is the noise divided by the average, and that we looked at. And if the Fano factor is above 1, it's bunching. If it's below 1, they call it anti-bunching. And for bosons, you get bunching. And for these classical particles, we get a Fano factor which is a bit less. So we say it's less bunching. But to truly look at the statistical properties of these particles, one will have to go
you could
further.
look at the statistical properties of the quantum model by plotting like a G2 correlation function or one of those
exactly.
kind of
We could.
and you could see whether that correlates with the difference that you see.
Exactly. One could either go. I guess these time depend. Like a G2 function would be a perfect thing to do. So we haven't done that. But that would be very interesting.
That is the difference, like that it is bunching that's...
Well, there's definitely a difference in the G2 function because you can express the noise in terms of the G2 function. Okay. So if the G2 functions were equal, then also the noise should be equal. So I guess we can still understand it in some way as bunching, but I don't know, I would really like to see multi-particle statistics to see bunching, that things kind of arrive in bunches. Yeah. And I think with just second moments, you don't really get there. You would have to go to higher moments to get a really convincing picture that things come in bunches or are more separated.
And then my second question was about exploiting this. So I know, again, do you know Defner's bosonic engine papers where he shows that bosonic statistics leads to an advantage when you have more efficient heat engines? If not, then my question doesn't really work. I'm just wondering.
No, but there's also a work from Lund where they also look at bosonic statistics and it seems to.
Because I would agree that bunching increases fluctuations, and then I guess the question is whether you can exploit that to make it something useful rather than detrimental. You were selling it as something detrimental. Yeah, so I think the papers were. Okay, so this is a bit speculative. I should look at these papers again, but I think these papers where they showed that kind of bosonic statistics is better is always kind of a pressure argument that you're dealing with. You have particles that are closer to each other because they kind of bunch, so they have a smaller pressure, and you somehow make use of that. If that's really then an advantage, if you compare to a homogeneous gas, for instance, and not n classical particles, and I'm not sure. Cool, thank you. I was only expecting a question because I can't remember the papers in any detail.
Okay, I saw a question there.
Yeah, Patrick, so I was intrigued by your result at the beginning of the talk about the link between signal to noise and dissipation. Maybe you can say a few words about this, because it doesn't match with my intuition, because if you consider, let's say, a QND measurement, there's no energy exchange between the system and the meter. So I actually never thought that there's any link between signal to noise and sort of how open the system is. At least, for QND systems. Can you say something about this?
So I'm not sure if one can adapt this to something like a projective measurement. Right. So this is really about, the result is really on currents. So let me maybe go back to this picture here. So if you have a classical rate equation, you can define certain currents. For instance, you can define the particle current that goes through the system. And then it's the signal to noise ratio in these kind of observables. If you want to measure a particular current, then you will see fluctuations. And if you want to have a high kind of signal to noise ratio, then it's beneficial if things dissipate a lot.
So is it equivalent to a difference between sensing position of an oscillator versus its energy, or how much pressure does it?
Yeah,
that's the reason, because I guess if you do a linear position detection, it's true it's not a linear measurement, then maybe there.
Yeah, I'm also not entirely sure if one could extend it to position measurements. I would have to think about that as well, because again, I don't really see how that translates into a current, how you can formulate it in as a...
It's like linear in A's and daggers.
Yeah. But I mean, these hold for classical systems.
Mm-hmm.
So you would need to look at a classical oscillator and the classical position measurement and formulate it in terms of current there. And generally, it holds for classical rate equations, which obey detailed balance, so kind of thermal baths, and also to overdamped Langevin equations. So it is quite a large class of models, but you can cook up classical models as well easily that don't obey this, so where you have some kind of memory effects or underdamped Langevin equations where you see some oscillations, and this can also break down.
I see, okay, thanks a lot.
Okay, one last question. Okay, if this is not the case, let's thank Patrick again. And thanks everyone for coming.